The complexity and challenges of UPF corruption model in low-power emulation. Abstract. The Unified Power Format UPF or IEEE 1801 is not just a language to denote a low-power intent or a power management specification for a design. It's a complete command set for verification and implementation of such low-power designs. UPF paved the way to accomplish the low power verification with a specialized simulator from very early stage of the design abstraction from RTL. These low power enabled simulators allows design instrumentation with a UPF artifact to mimic the accurate low power behavior at power up-down cycles, where, for example, the input and sequential logic in a low power down domain needs to be corrupted onto unknown, that is, X, or propagated S from OFF to on domain, or analyze X state initialization of legs after power up. So evidently, 4 state logic value 0, 1, X, and G are essential for accurate low-power logic functional verification. However, capacity limit and event-driven execution mechanism makes simulator almost impossible to realistic workloads with multi-path power sequencing and huge power management architecture at high speed. Hence, hardware emulators comes into play because they are cycle-based, runs very fast in megahertz range, accommodated with large design, 10 billion gauge SoC, and obviously the best suit for running realistic low-power workloads. However, emulators are made of silicon and only allows 2 state logic values, 0 or 1, which makes UPF-based verification very challenging. In this paper, we established the orchestration of the industry, the first 4-state logic-based hardware emulation technology that not only simplified UPF-based design verification, but also significantly shortened the verification around turnaround time with real-world power management workloads. Chapter 1 Introduction. The IEEE 1801 standard specifies the low power intent, that is, UPF for any design. The UPF is the ultimate abstraction of low power methodology today. It provides the concept and artifact of the power management architecture, the power-aware verification, and low-power implementation mechanism for any design. It provides the notion of the power architecture from very early stage of design abstraction. Now, it's the industry trend and standard for lowering static and, in some special cases, dynamic power dissipation in every digital design. Overwhelming. UPF stands out as the only alternative choice of lowering power dissipation when fabrication process technology advanced below 65 nanometer. Now, almost all SoC today heavily utilize the UPF for a power management and low power implication. These SoCs are enormous in size, typically comprise of 8 to 10 billion gates, which consumed 60 to 70% of design effort in verification and easily hit the capacity limit of the most verification tool and makes design verification turnaround time miserably long. On the contrary, today's data center class emulation systems are highly scalable in terms of design capacity, scales up to 10 billion gate design, and it can run accelerated simulation up to 4 MHz speed on hardware. Furthermore, the emulation allows realistic loads for UPF-based designs. For example, emulation allows multi-pass power sequencing workload compared to single-pass in simulation. This enables complex interaction scenarios and repeated power state entry, retain or exit with a diversified set of external stimulus. Figure 1 shows the diagram of today's data center class emulator. Generally, UPF-enabled emulation-based low-power verification flow is suitable for long-running directed tests that do not require complex test bench interaction. Specifically, the UPF verification comprises of power management, BIOS, firmware, OS, and application-level workloads. Naturally, thousands of hierarchical scope-based UPF files required to process, overlay, supply network circuitry, and instrumented design with all types of low-power components like low power supply network, power switches, isolations, level shifters, repeaters, retentions, corruption mechanism, and so on. The figure 2 shows the UPF-enabled emulation verification flow. The UPF LRM defines the corruption as the rules defining the behavior of logic in response to reduction or disconnection of power to that logic. Obviously, applying UPF to any design requires additional functionality to model the power supply network, corruptions of logics, signal values, and etc. And when a sufficient power is applied for normal operation as well provide additional functionality for propagating, saving, and restoring of the system states. Corruption is a situation where the value signal become unpredictable at power off or below predefined threshold values. A corrupted signal is represented by assigning a particular value, generally x, in 4 state and 0 or 1 in state logic representation. Feature 1. Data center class 3-rack emulator, and figure 2, UPF-enabled emulation verification flow. It's important here to reference 4-state and 2-state logic value definitions from System Verilog SV LRM. The SV logic value set consists of the following 4 basic values. 0 represents the logic a 0 or false condition. 1 represents a logic 1 or a true condition. X represents unknown logic value. Z represents a high impedance state. So the values 0 and 1 are logical complements of one another. When the G value is present at the input of a gate or when it is encountered an expression, the effect is usually the same as an X value. The SV data types that can have an unknown X and a high impedance G values are called 4-state, which can store 4 logic values. All bits of 4-state vectors can be independently set to one of the 4 basic values. These are logic, lag, integer, and time. The other types do not have unknown values and are so called and are called 2-state types, for example, bit and int, which only store 0 or 1 values in each bit of a vector. Tight conversion between 4-state and 2-state can be automatic from a large number of bits to a smaller number of bits involve truncations of the most significant bits, MSBs, as when a 4-state value is automatically converted to a 2-state value, any unknown or high impedance bits shall be converted to zeros. Hence, it's distinctive that a design under test with a UPF mandated to coordinate the situation for unknown or X initialization, corruption to X, and propagation to X as well high impedance or G condition. It's also true that the emulators are the best choice for realistic UPF or low power workloads, specifically because of a very quick turnaround time and very large design capacity accommodation compared to the conventional simulators. However, the problem is emulators are developed on custom ASIC with hundreds of processing units on physical boards, like shown in Figure 1. Essentially, they are hardware on silicon and by default capable of handling only 2-state, that is 0 or 1 logic. This signifies that the fact that many low-power functional verification features like corruption to unknown, initialization to unknown states, propagation of unknown, as well analyze the strength resolution will be either impossible to implicate on hardware or have to extrapolate 0 or 1 onto X, that is, 2 device unknowns, by some sort of faking mechanism. However, as logic verification engineer, we know that the inherent meaning of initialization to X, corruption to X, propagation of X are not just about faking or mapping 0 or 1 onto X for low power implication, visualization, or facilitating debugging. It's on one hand properly modeling logic and reg data types because integer and time may not involved in low power designing, according to SV and the UPF LRM, and on the other hand properly handling human perception of logic verification and or implementation mechanism that introduces the notion of the X-pessimism or X-optimism used in emulation hardware. Evidently, emulation and 4-state logic values are prominent for UPF-based low-power verification. However, there are a multitude of complexities and numerous challenges in challenging 4-state, specifically UPF power-related implication like corruption mechanism in hardware. A. Motivation and contribution of this paper. Our core objective is accurately define the inherent characteristics of UPF-based low-power verification flow. We systematically identify today's chip design and verification methodology and approach the limitation of existing highly efficient hardware emulation verification platform. So in this paper, we identify the requirement of 4-state logic in UPF-based emulation flow, identify the complexity, and establish the orchestration of industry-first 4-state logic-based hardware emulation technology that not only simplify the UPF-based design verification, but also significantly shorten the verification turnaround time with real-world power management workloads. We hope this paper will serve a reference point for innovative research and realizing of a highly efficient hardware emulation-based low-power verification platform. B. Organization of this paper. This paper is organized as the following structure. Section 1 introduces the key concept and relevant UPF verification concept and flow. Section 2 is explain the fundamental of the complexity of UPF verification on emulation. Section 3 provides further insight of four-state logic and orchestration in emulation. The final section 4 draws the conclusion and points further and future research perspective. The reference are shown at the end. Section 2, Fundamentals and Complexities of UPF Verification. In Section 1, we explained how UPF verification concept and four-state logic are correlated. We also understand that the inherent meaning of the initialization to X, corruption to X, and propagation of X lies in the fact that how SV logic and reg data types are modeled in verification tools and how notions of the X-pessimism and X-optimism duals plays vital roles in realizing them in emulation hardware. Let's step back and understand what X-pessimism and X-optimism duals are. First, we have to look for the source of the X in the design. The primary sources of the X in UPF and its power down phenomena are logic, reg, and etc. and in the UPF and non-UPF both. Explicit assigned to X an initialized state element, legs with the without rest, reset, and etc. The secondary sources could be an incomplete SV assignment, like a missing default statement in case blow up, both conflict, and out-of-range bits and part select, indexes in MDA, arithmetic concept, divided by 0 and modulus 0, and etc. Some of these and interpreted in verification tools may differ in actual design implementation in hardware. The notion of X-optimism comes from the fact when verification tools generate 0 or 1 signal values when they are actually unknown X. Similarly, pessimism comes when tools produce X whereas they should be known 0 or 1. These verification tools results may be far different when the RTL design is actually implemented, synthesizes into get-level netlist, which is widely known as simulation synthesis mismatch, where X is don't care in the synthesis, but in simulation, X is a logic value distinct from 0, 1, and G. There. A. UPF corruption model. In regular HDL-based functional verification simulation world, and presume that all logic are powered on at the beginning of the simulation and remains powered on throughout the verification cycles. However, the SoC designs today are far more complicated by adopting multi-voltage, power gating, state data retention, as power standby, even dynamic voltage scaling techniques on same chip, virtue of UPF as shown in Table 1. Table 1, a complicated power management schemes on chip. Multi-voltage, power gating with retention, low power, standby, DVS and AVS. These power management features definitely alter and/or instrument the actual design with additional power artifact like confinement of different design blocks on two different voltage region power domain, provide different supply network and sources, a power switching control network, power management cells like isolation or retention, power down corruption semantics, and so on. Fortunately, today's low power enabled verification tools, simulators and emulators allows design instrumentation with a UPF artifact to mimic accurate low power implementation like behavior at functional verification level. Among all, corruption modeling imposes a complete unprecedented requirement from HDL logic values as well impact on design instrumentation. In low power, corruption refers to a situation where the value of a signal becomes unpredictable when the power supply for the element driving that signal is disconnected. Changes to off or drops below some threshold, corruption of a signal is represented by assigning the particular values to a signal. It could be X or 0 or 1, but probably not the floating. The corruption value depends upon the type of signal, and rare cases may also be user-definable. It is typically applied to signal drivers and propagate all sinks of that signal that are not isolated from their sources. When a design instance is turned off, every sequential element within the power down instance and every signal driven from within the power down instance must be corrupted. As long as the power remains off, no additional activity takes place within the power down instance. All processes within the powered down instance become inactive regardless of their original sensitivity list. Events that were scheduled before the power was turned off and whose target is inside a powered down instance have no effect. So when a design instance is turned on or restored, corruption of a sequential element and signals within the powered down element ends. Continuous assignment once again becomes sensitive to changes to the right-hand side of expressions, and other combinational processes such as an orange_combo blocking system value resume their normal sensitivity list operation. All continuous assignment and other combinational processes are evaluated at power up to ensure the constant values and current input values are properly propagated. Sequential elements are evaluated on next cycles after power up. B. What could be the corruption values? Signals are corrupted by assigning them to their default values, such as X for the 4 state types. The SV LRM denoted that the 4-state and 2-state data types of default initial values are X and 0 respectively. So any design that have 2-state and 4-state data types. 2-state signals, that is bit, continue to operate as 2-state initially to 0. 4-state signals, that is, for example, logic and lag, continue to operate in 4-state initially to X. Initialized to X. The question may arise for interoperation between 2-state and 4-state data types. The answer can be found in the SV LRM as noted in section 1, and type conversion between 4-state and 2-state can be automatic from a large number of bits, a smaller number of bits involving a transaction of the most significant bits, MSBs. And when a 4-state value is automatically converted to state value, any unknown X or high impedance bits shall be converted to 0. During the low power verification, if the driver of an alias is powered down, the output of the driver is corrupted, and this corrupted value propagated to all things over the net. To understand the corruption occurs in a given design, it is necessary to recognize the element of design represent or contain driver. In the RTL code, any statement involving arithmetic or logic operations or conditional execution are interpreted as represent drivers and cause corruption when powered down. Unconditional assignment and Verilog, both primitives do not represent drivers and therefore do not cause corruption when powered down, but they may propagate corrupted signals from upstream drivers. C. Simulation emulation congruency. It is now distinctive that corruption modeling along with other power implications specifically for accurate mimicking low power behavior at a power down, a power up, down cycles, where, for example, the input and the sequential logic in a power down domain needs to be corrected one to values, that is, x, or propagated x from off to on domain, or any analyzed x state initialized for a sequential element after power up. Even the combination logic within the power down domain needs to evaluate it to x. Conventionally, corruption model is based on four-state logic and easily accommodated in event-driven low-power simulation environment. However, emulation is devised on actual silicon hardware, customizing, and there is no unknown or X state in hardware. This makes low-power corruption modeling as well as low-power verification, that is wave-based debug, extremely difficult. For example, we utilized the 0 or 1 or random or inverted mechanism for two-state UPF emulation flow. This may be applicable for both power up and power down state as follows. Power down state, high, low, random, inverted. Power up state, high, low, random, inverted. Consequently, users have to assign and maintain specific power down values throughout the entire verification flow. Arguably, it's possible that the simulator can tag or debugger can fake a power down corruption value to X, but that's completely for the sake of a visualization. Actual X corruption, propagation, initialization, or evaluation is not possible in two-state environment. The figure 3 shows the default two-state corruption, and figure 4 shows the four-state corruption in the debugger waveform windows, as well. Figure 5 shows. Figure 3, emulation two-state showing a 0 during a power down and random after power on. The figure 4 and emulation 4 states showing S during a power off, and the debug design reinitializes as needed after power on. The figure 5 simulation, which are generally 4 states showing X during power off, and design reinitializes as needed after power on. From these 3 figures, it's evidence that a 4-state emulator corruption model to X is expected and matches the corruption behavior of simulators. Hence, 4-state corruption model also possesses the advantage of directly compare the result between simulation and emulation. Apparently, the 4-state emulation and simulation result appear congruent in UPF-based regular SV reg-related corruption mechanism. However, actual implementation and/or realization of 4-state logic in emulation could have differences. Preliminary, because of X-pessimism and optimism and subtle difference how RTL level and GAL level netlist level design interpret there's X-pessimism, optimism duos. Because emulation learns tons of every RTL design to solve level design through spatial synthesis process, which are more close resemblances of the design is actual hardware chip implementation. Hence, the emulation and simulation will not congruent in presence of the X and the region is further explained below. Simulation has three modes of operation: SV LRM mode, default, CAT, compute as ternary mode, optimism and similar to how hardware propagated X. Fourth, forward only X, mode more pessimistic, forwarding of X. Emulation will only adopt a similar mechanism of simulation CAT mode because emulation transformed the RTL design onto the gain netlist by synthesizing. In addition, SV LRM strictly applicable for all the RTL designs. Note that two equivalent RTL implementation will handle access differently in LRM simulation mode. However, two equivalent RTL that result in the same gauge will have the same in the emulation. The experimental analysis of the UPF-based emulation congruency. Although the previous section provided detailed difference based on X-optimism pessimism duo, this section will summarize the UPF-based and simulation and emulation similarity and dissimilarity based on four logic corruption models. So the table 2 and 3 shows our empirical data for corruption mechanism comprising of simulator, two-state, and four-state emulator. Table 2. Comparative studies for sequential element of power sequence comparison for a simulator and emulator. Design updated power input of power domain, output, latches, flip-flop, and lax memory. Simulator, two-state emulator, and four-state emulator. The experimental in table 2 considers all design objects are part of power domain in a UPF-based verification setup as shown in the first column. The sequential element latches and flip-flops and the memory instances emulation two-state corrupt sequential element based on a special UPF command and options. The create power domain, blah 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 blah. The domain name and power underscore down underscore states, power minus power underscore up underscore states. That allows the user to select corruption or normal values at a power up and a power down in the third column. However, four-state reserved for every sequential element, latches and flip-flops as well every signal element driven from within the power domain design will be corrupted to F. There are little difference in the corruption mechanism in a memory between the simulation and emulation. Corrupt X versus memory wrapper model because memory is modeled and treated and implemented differently in a simulation and emulation. The subsequent section explains the detail on UPF-based corruption and mechanism and emulator from modeling and implementation perspective. The table 3 comparative studies of logic states and corruption semantics for simulator and emulator, runtime constraint and observation outcome, run condition, power state, design object, simulator and two-state emulator and four-state emulator. The experiment in table 3 consider for all design objects are SV and lag data types. Some of them are ordinary lag and some of them are especially lag with the UPF data and state retention capabilities. It also having the design object as a primary input and output I/O of the power domain. The power state column shows the power on or off or on to off or on off to on situation. The result clearly shows there is no differences in the result in between simulation and four-state emulation, except there is an S to the position at a time 0 after swap in row. After swapping in row. Here, the position only works at emulation, hence the reg remains X at time 0 for simulation until reset is asserted, while 0 for four-state emulation. So it's obvious congruence works in a simulation and emulation four-state. In UPF corruption modeling force represent unknown. Section 3. UPF four-state logic orchestration in emulation. In previous section, we noticed that experiment data in table 1 shows a little difference in corruption mechanism in memory between simulation and emulation, corrupt to X versus memory wrapper model, because memory is models treated and implemented differently in simulation and emulation. In this section, we will identify the difference and explain the reason the experiment and analytical data. A. Impact of memory and FIFO in UPF-based emulation. When a power domain is shut down, the contents of all logics including the memories and FIFOs are set to 0x, and it is comparatively easy to implement in simulation. However, as I noted earlier, corruption of or X modeling in emulation is very costly because it needs to model in hardware. The alternative choice could be to setting all power down logics to some random values. While it is relatively easy to set registers to random values inside a power down domain, it is quite difficult to set up memories and FIFO content to random values. The one approach is to load the content to memories and FIFOs with predefined randomized values, but the load operation can be time-consuming due to the large number of memories and FIFOs that are in powered down domains. Another approach is to create external logic various triggers when the power domain is in shutdown mode. This external logic will update the memory and FIFO content in estimation speed. This approach usually requires additional hardware resources, requires code development for an emulation platform, and also requires additional debug to make sure that it functions correctly. Ultimately, none of these worked as efficient as the flawless mechanism for memory and FIFO corruption. Instead, in UPF 4 state, we introduce the automatic memory wrapper in hardware and do not have runtime cost to implement. Memory wrappers help models in behavior of design memories correctly and specifically when there are access on the address or control signals or memories. Without the pairs access, these control signals of memories are interpreted as 0 for non-bit rest memories. Figure 6 memory corruption results at power down without a memory wrapper. And here in figure 6, the memory was written 00001111. During 4 of the out shows X, however, dumping the memory content shows 0:ff/0000FFF1111, which signifies the content of memory is not actually corrupted. Figure 7. Memory corruption result at power down with the memory wrapper. Here, figure 7, the memory was written exactly same to 00001111. During power of the out shows X as well. Dumping the memory content also shows 0:FF XXXX XXXX which signified that the contents of memory is properly corrupted. This result matched with the simulation and desirable verification mechanism for memory during power down. Section 4. Concluding remarks. The UPF-based low-power designs are prevalent today in every chip designed and manufactured today. The demands and expectation for four-state emulation in the low-power design verification industry is eternal. This paper identified the complexity and challenges of UPF-based low-power design verification on emulation platform through corruption modeling. In the abstract and extended abstraction section, we approached the rudimentary parts of low-power verification. So we explained the requirement for state logic and primary bottleneck for implication, the four-state logic in hardware emulation platform. So we also presented the empirical data that shows the comparative studies of logic state and corruption semantic as well as sequential elements and power sequence comparison between simulator and emulator. This evidently shows the potential and importance of four-state in hardware emulation platform. In our future research plan for UPF corruption model in low-power emulation, we want to extend our studies to further understand the capacity and the performance impact of corruption in four-state and versus two-state logics. More specifically, the influence and contribution of corruption model in terms of emulation capacity or gate size during build time and performance in clock frequency during runtime. Acknowledged, the authors would like to express sincere gratitude to the reviewer from the Cadence Design Systems for providing useful insight and guidance in conducting research and preparing this paper. There are two references here, and I read today this paper, Complexity and Challenges on UPF Corruption Model in Low Power Emulation. Thank you for your time, and see you next time. Thank you again.